Let us explore Dijkstra's algorithm, the classic method for finding shortest paths. Dijkstra's algorithm solves the single-source shortest path problem on a weighted graph whose edge weights are all non-negative. That single sentence contains nearly the entire contract of the algorithm. Single source means we choose one starting node, usually called the source. Shortest path means we want the minimum possible sum of edge weights along a route. One run computes the best distance from the source to every reachable node. Weighted graph means edges have costs, such as distance, time, money, or latency. And non-negative weights means every edge cost must be at least 0. To make this concrete, imagine a road network drawn as a graph. The vertices are cities, the edges are roads, and each edge weight is a travel time. Let city A be our single source, the node every shortest path starts from. From this one source, Dijkstra's algorithm answers two questions. First, what is the minimum travel time from A to each reachable city? We keep track of distances. Second, which sequence of roads achieves each minimum? We keep track of the previous city, so we can reconstruct the route. The first answer tells you how expensive the best route is. The second tells you which route achieves it. Let us understand Dijkstra's algorithm through a conceptual analogy. Imagine dropping a pebble into perfectly still water. As a wave propagates outward from the center, it reaches nearby locations first, followed by more distant ones. Dijkstra's algorithm behaves similarly. It starts at the source node and gradually expands outward, always visiting the closest unvisited node before moving on to nodes that are farther away. At any stage, the algorithm divides the nodes into 3 groups. Finalized nodes are the nodes whose shortest path from the source is final. Discovered but not finalized nodes are the nodes that are discovered, but whose shortest path from the source is not yet finalized. Unreached nodes are the nodes that are not yet reached. The next node chosen is the discovered but not finalized node with the smallest tentative distance from the source. Here B has distance 2, while A has distance 4, so B is chosen. That choice is the core greedy step of the algorithm. From the set of nodes that are not yet finalized, select the one with the smallest tentative distance from the source. Finalize that node. Its tentative distance is now its shortest distance. Here, that node is B. Because all edge weights are non-negative, any path through an unfinalized node with a higher current cost cannot produce a shorter path to this node. We then relax B's outgoing edges to lower the tentative distances of its neighbors. Going through B improves A from 4 to 3, and discovers D with tentative distance 6. After one greedy step, S and B are finalized, A and D form the discovered frontier, and C and E remain unreached. The next iteration will choose A, because 3 is the smallest tentative distance. Dijkstra's algorithm does not construct the entire shortest path at once. It incrementally expands a set of nodes with finalized shortest path distances by repeatedly selecting the not yet finalized node with the smallest tentative distance from the source, declaring that distance final, and then relaxing its outgoing edges to lower the tentative distances of its neighbors. Because all edge weights are non-negative, each greedy finalization is safe, and the finalized region expands one node at a time, like a wave moving outward. Now let us watch the lazy implementation of Dijkstra's algorithm run, one line at a time. On the left is the algorithm. In the middle, the same weighted graph from the analogy, with S as the start node. Below the graph is the distance array, and on the right, the priority queue. These are the only 2 pieces of state we need. First, the distance array. Every entry starts at positive infinity, because we assume every node is unreachable. Then the priority queue. It holds distance and node pairs, ordered by the smallest distance, and it starts out empty. We assign a distance of 0 to the start node, S, and we insert the pair 0, S, to say we intend to visit S with a best distance of 0. Now the algorithm begins. We loop for as long as the priority queue is not empty. Top returns the heap's minimum and pop removes it. The pair 0, S, distance 0, node S. Now compare the pop distance D with dist of U, which stores the best known distance to U. 0 equals 0, so we enter the block and process S. Now we walk every edge leaving S and relax it. The edge to A costs 4. 0 plus 4 is better than infinity. So A's best distance becomes 4. Every successful relaxation appends a new pair to the Q, so 4, A goes in. The edge to B costs 2, so B's distance drops from infinity to 2, and 2, B joins the Q. With every edge of S relaxed, we go back to the top of the loop. Top returns the heap's minimum, which is 2, B, and pop removes it. The popped distance matches B's distance in the distance array, so B is finalized at 2. Going back to S cannot help, because S is already finalized at 0. But the edge to A costs only 1. 2 plus 1 is 3. Better than the 4 we already had. So we push 3, A. But look carefully at the Q. The old pair, 4, A, is still sitting there. A standard priority queue cannot update a key in place, so instead of hunting for the old pair, we simply insert a new one and throw the outdated one away later. That laziness is what names this implementation. B's last edge costs 4, so D is discovered at distance 6. 3, A comes out next, and 3 matches the distance array, so A is finalized at 3. A's edges back to S and B lead to nodes that are already finalized, so neither can be improved. The edge to C costs 5, so C is discovered at distance 8. Now the interesting case. 4, A comes out of the queue. But the distance array says A is already 3. 4 is not equal to 3, so the better route through B supersedes this pair. The condition fails, so we never enter the block, and the pair is simply dropped. That one condition is what keeps the lazy implementation practical. Outdated pairs are discarded the moment they surface. 6, D pops out. The pop distance matches D's distance in the distance array, so D is finalized at 6. Here is the payoff. The edge from D to C costs just 1, so 6 plus 1 is 7, which is better than the 8 we found by going through A. And the edge to E costs 5, so E is discovered at distance 11. 7, C pops out. The pop distance matches C's distance in the distance array, so C is finalized at 7. From C, the edge to E costs 3. 7 plus 3 is 10, which improves E from 11 down to 10. 8, C is stale, because C is already finalized at 7. Skip it. 10, E is next, so E is finalized at 10. Both of its neighbors are already finalized, so nothing improves. One last stale pair, 11, E, is thrown away, and the queue is finally empty. The loop ends, and we return the distance array. Every entry is now a final shortest distance. S0, A3, B2, C7, D6, and E10. The relaxations that survive trace the shortest path tree. There are only a few moving parts. The distance array holding the best distance found so far, the priority queue telling us which node to visit next, and the staleness check that discards outdated pairs. Because every relaxation can push one pair, the queue holds at most E entries, which gives the lazy implementation a running time of order E log V. We can now find the shortest distance to every node. But which roads actually achieve it? The distance array answers how much the best route costs. It says nothing about which route that is. Recovering the route needs just one extra fact per node, which node we arrive from. Here is the same graph again, with 2 arrays underneath. The distances we already know how to compute, and the new parent array. Every parent starts at a sentinel, because we have not arrived at any node yet. And here is the only change to the algorithm. One line, inside the relaxation we have already seen. Whenever a relaxation lowers the distance to V, the node we came from must be the best way to reach it, and we record that parent with it. Let us replay only the relaxations that succeeded, in the order Dijkstra performed them. S starts at 0. From S we reach A at 4 and B at 2, so both record S as their parent. Now watch what happens when a better route appears. Going through B, A drops from 4 to 3. A's parent is overwritten from S to B, and the amber edge moves with it. The parent array always holds the best arrival we know of. B also reaches D at 6, and A reaches C at 8. Then D finds a cheaper way into C. 6 plus 1 is 7, so C's parent flips from A to D. D reaches E at 11, and then C improves it to 10, so E's parent flips from D to C. Every node is finalized, and the amber edges are exactly what the parent array describes. A tree, rooted at S, holding one best root into every node. So to recover a route, we do not need to search at all. We just read the parent array backwards. First, check the destination is reachable. If its distance is still infinity, there is no route to return. Otherwise, start at the end node. Let us ask for the route to E. E's parent is C, so we step to C. C's parent is D, so we step to D. D's parent is B, and B's parent is S. S's parent is the sentinel, which is how we know we are at source node. The loop stops. We collected the nodes from the destination back to the source, so the sequence is reversed. Flip it, and there is the route. And the edges along it add up to exactly the distance Dijkstra computed. 2, 4, 1, and 3 make 10. One extra array, one extra line, and the algorithm answers both questions. How far, and which way? The lazy implementation works, but it leaves outdated pairs behind. Let us fix that. On our small graph, the lazy version pushed 9 pairs and popped out 9, and 3 of those were stale. On a dense graph that gets much worse, because every relaxation adds another pair the queue must carry and eventually throw away. The fix is a different data structure, an indexed priority queue. It keeps at most one entry per node, so a duplicate can never exist. Because it is indexed by node, it can tell you in constant time whether a node is already inside, and lower that node's value in logarithmic time. So instead of inserting a second pair and dealing with the old one later, we simply update the entry that is already there. Same graph, same distance array. Only the queue on the right has changed. Notice the pairs are written node first, then distance, because this queue is indexed by the node. We start exactly as before. S gets distance 0 and goes into the queue. We poll the minimum, S, at distance 0. And here is the first thing that vanished. The lazy version needed a condition to test whether the popped pair was stale. This one does not, because a stale pair can never be created. So we go straight to relaxing S's edges. The edge to A costs 4. 0 plus 4 is better than infinity. A is not in the queue yet, so we take the insert branch. B costs 2, so B's distance becomes 2, and B is inserted as well. B is the minimum at 2, so it comes out next and is finalized. The edge back to S cannot improve anything, since S is already finalized at 0. But the edge to A costs 1. 2 plus 1 is 3, better than the 4 we had. This is the moment that separates the two implementations. A is already in the queue, so we take the other branch, decrease key. The row for A is updated in place from 4 to 3. No second pair, nothing left behind. At this exact point, the lazy version pushed a second pair and left the old one to be discarded later. The eager version just rewrites the row it already has. B's last edge costs 4, so D is discovered at 6 and inserted. A is the minimum at 3, and it is finalized straight away. There is no stale copy of A to trip over. A's edges back to S and B lead to finalized nodes, so neither improves. The edge to C costs 5, so C is inserted at 8. D comes out at 6 and is finalized. Now the edge from D to C costs only 1. 6 plus 1 is 7, which is better than the 8 we found through A. C is in the queue, so decrease key again. Its row goes from 8 to 7 in place. And the edge to E costs 5, so E is inserted at 11. C comes out at 7 and is finalized. From C, the edge to E costs 3, so 10 is better than 11. One more decrease key, and E's row drops from 11 to 10. Finally, E comes out at 10. Both of its neighbors are already finalized, so nothing improves, and the queue is empty. The loop ends and we return. Same distances as before. S0, A3, B2, C7, D6, E10, and the same shortest path tree. Now let us compare the two versions. The lazy run inserted 9 pairs and threw 3 away. The eager run inserted 6 and updated 3, and wasted nothing. Both produce the same answer. The eager version simply never creates work it has to undo, which is why it is the better choice on dense graphs. With an index binary heap, this runs in big O of E log V, swapping in a d-ary heap, with d equal to E over V, speeds up all those decrease key operations further. And a Fibonacci heap gives the best known bound, though its constant factors make it impractical until the graph is very large. Let us put the whole algorithm back together in one picture. Dijkstra's algorithm finds the shortest path from a single source to every other node, and it needs every edge weight to be non-negative. It works greedily. Repeatedly take the unfinalized node closest to the source, declare that distance final, and relax the edges leaving it. 3 pieces of state carry the whole algorithm: the distance array, the parent array, and the priority queue that decides what to visit next. The lazy version pushes a duplicate pair on every improvement and skips stale ones on the way out. The eager version keeps 1 entry per node and lowers its distance in place, so no stale pair is ever created. Either way, with a binary heap, the running time is order of E log V. Thanks for watching.